This is Dr. Holt. I want to work 3 problems regarding angular momentum. The first problem, I have a uniform bar of length 0.96 from here to here. It has a mass of 0.89. It's going to be pivoted at one end. Here I have a small mass of 0.3 kilograms. It's coming across horizontally at a velocity that we do not know. It's going to strike a distance of 0.8 times 0.96 from the rotational point. And our objective here is to find that velocity. To work that problem, we start out as an energy problem. You want to do the potential energy at impact, say at AI, plus the kinetic energy at AI must equal the potential energy final plus kinetic energy final. Now, as this thing swings up, the kinetic energy here is going to go 0, and we're going to let the potential energy here go to 0 also. So what we want to do here is to find out what the, we're going to work this part first here. We're going to find out what is the potential energy as it swings up. So we'll draw a little sketch here. This is the position it is right now at the small mass. It's going to be stuck right here. And now that is going to rotate up a 60-degree angle up to here, like this. And again, that little mass is just clone it, move it into position approximately like that. And again, this angle here is going to be 60 degrees. Alright, now the key to this is to find out how much we've risen as we went up 60 degrees. So we want to find this distance here. And the other distance we're going to be looking for is the center of mass shift of the uniform bar, which is going from here to approximately here. So again, I'm going to draw that line as coming off this way here, and then coming off this way here. Alright. Now the distance from here to here is going to be 0.96 times the 0.80. And if we run that number, that's going to give us 0.768. So that distance is 0.768. Let me get a different eraser. Go back to that. Use a smaller little eraser, and that'd be 0.768. From here to here. Now the center mass is going to be half of the distance of 0.96. So we're going to call that distance to be 0.96 divided by 2 from here to here. So the potential energy is going to equal to mg. So we'll do the small mass first. It's going to be 0.30 times 9.8 times 0.768 minus 0.768 times the cosine of 60. Again, that distance there represents the distance from here to here. This distance right here would represent this. Again, I'm taking this length here, I'm subtracting this length here times the cosine of this angle. That would give me this value here. Alright, now the other one, we'll do this mass, the other one, and that's going to give us plus the 0.89 times 9.8. I'm going to slide that all over because I'm running out of a little bit of room. Let's see, let's grab this guy. Like this, and then we do times 0.96 divided by 2, which gives me the center mass, minus 0.96 divided by 2 times the cosine of 60. Now if you run that number, you will find out what your potential energy final is. And I figured out the potential energy final is equal to 3.222. Alright, and again that would be in joules of potential energy. Alright, now we know after impact, when this particle is going in, we want to find the kinetic energy right at this point. So the kinetic energy at impact must also equal to 3.22 joules. So we can set 3.22 joules equal to I 1 half I times omega squared, because this particle now has stuck. To find the moment of inertia, we take a rod that's pivoted about one end, and that's going to give me 1/3 times its mass, which is 0.89, times its length, which is going to give me 0.96. We're going to square that, plus the mass, times the distance it is from the rotational point, which is our 0.768. We're going to square that. That's going to give us a total moment of inertia of 0.45. And that would be in kilograms times meters squared. Alright, so there's our inertia value here. And again, we know our energy value here. So we can solve for omega. So we can put 3.222 joules is equal to 1/2 times 0.45 kilograms meters second times omega squared. We can solve for omega here, and we will get omega is equal to 3.78 radians per second. Alright, now we know that we're going to get conservation of angular momentum. So we're going to find out what the angular momentum was right before impact and set it equal to the final angular momentum. So since this is treating this as just a point mass here, we're going to take its mass, which is 0.30. We're going to multiply it by its velocity, which we don't know right now is VI, and again from the rotational point is 0.768 away. We're going to set that equal to I times omega. Now again, I is going to be this value here, our 0.45 times our omega of 3.78 radians per second. We solve for that, VI, and we will get VI is equal to 0.45 times 3.78 divided by 0.30 times 0.768, and we'll get VI approximately 7.39 meters per second. Alright, that's the first problem I want to solve. Alright, let's look at another one. Our second problem is this figure here. Now this figure is this is an interesting problem because it is not it's free to pivot here. Now the problem is this is an elastic collision here, and then the sphere is at rest. It does not stick. So this is an elastic collision. So this object here is going to rotate around its center of mass, but now as it hits, it's also going to have velocity this way. So it's going to move this way and it's going to rotate the same way. So typically if I do or just do a quick sketch to kind of show you what I mean by this. After this object, we're going to rotate around. This object will have velocity going this way. It will also be rotating around like this. This is the after condition. Now this little mass here is just going to be here. It's going to stop. This velocity, this is going to have zero velocity. It says in the problem the collision is at rest. All right. Key words: elastic collision. So we can set up our kinetic energy equation. Initial is equal to our kinetic energy final. So we can go back and say that 1/2 the little mass times this velocity squared must equal to, after it hits, 1/2 times the moment of inertia of this times its angular velocity squared plus 1/2 times big M times V final squared. Well, this is the VF here. So right there is our energy equation. I would go ahead and simplify things, get rid of our 1/2. Now I'm going to go back and calculate the moment of inertia. The moment of inertia about a rod that's spinning around its own centroid is going to be 1/12 big M, the mass, times the length squared. Okay, so there's the moment of inertia here. So we'll keep simplifying this equation. We get mv squared is equal to 1/12 big M times L squared omega squared plus big M times VF squared. Alright, other things we know. We know since elastic, we know that the linear momentum must be same. PI must equal to PF. So our initial momentum linear is going to be little m times V, and that must be equal to big M times VF. I will take this problem here, I'll solve for VF. VF is going to equal to little m times V over big M. Alright, so we're going to hang on to that one right there. Alright, because what I'm going to end up doing is I can probably substitute that back into this equation, or for VF right there. Alright, so let's keep on going. Let's go to angular momentum next. Now, angular momentum, we know that Li is going to equal to Lf in this case. So we go back and we say it's going to be m times little v, and let's look and see if it gave us a value for d. Yes, it did. It said the sphere moves right and it hits 1/4 L. So this distance is 1/4 L. So we'll multiply that by L over 4. Okay, we will set that equal to I times omega, which will give me 1/12, which we already figured, of m L squared times omega. Alright, now what I would do with this one would be I would start simplifying here if you can. I can cancel out this L here, and I can cancel out this L here. I'm also going to multiply this side by 4 and multiply this side by 4. I'll lose my 4's here and here, and this will cancel out here, and this gives me a 3 here. So when I rewrite that, do I not get MV is equal to, make sure to, let me clarify, that's little m. I don't want to get confused about big M. Little m times V is going to equal to 1/3 big M times L times omega. From this equation, I'm going to solve for omega. So can I say that omega is going to equal to 3 little m V over big M L. Alright, so now I'm going to take this and we're going to go back to the kinematic equation that we had, and what we had here, I'm going to see if I can grab this and bring this down, and we'll start substituting back in, and we should have the problem done. I'm going to grab this part right here. I'm going to copy that, bring it down here, I'm going to paste it, bring it down to here. Alright, I'm going to take VF out of here and replace it with this, and we've got to make sure we square that. That gives me little m squared big V squared, sorry, not big V, but little v squared over big M squared. Okay, I go back here to omega. I'm going to slide, see if I can slide some of this over, maybe. I don't know if it'll let me or not. Let's see. Slide this over. Nope, can't do that. Let's just, I'm going to rewrite it because I want to do plus M. I just need some more space to put things in. Alright, now we're going to take out omega here and replace it with this. I'm going to square this as I go along. That's going to give me 9 little m squared V squared over big M squared L squared. Alright, let's see if we can start simplifying a lot of stuff, because it looks like we can. I got a big M here. I'm going to take that out here, and I take off the 2 here. I got an L squared here. I can take that out and take that out here. Over here, I can cancel out, let's see here, I can cancel out this M here and cancel that out here. Let's see what else I got here. I got a V squares here, here, and here. Let's see what else I got. We're getting there. I got M here, We'll cancel out this one and cancel out this one here. Alright, so anything else I can do here? Alright, let's rewrite and see what we have over here. So on this side, I've canceled out everything, so I have a 1 here. Here I have 9 over 12 of little m over big M here. Plus over here, I'm going to have little m plus big M here. So 9 divided by 12, divide each of those by 3. That's going to give me, what's that, 3/4. So I got 1 plus, 1 equals. 1 equals 3/4 little m plus big M plus little m over big M, and 3/4 plus 1/4, that gives me 7/4. So 1 is equal to 7/4 little m over big M. Multiply both sides by 4/7, and we get 4 over 7 is equal to little m over big M. All right. So kind of a challenging problem, but again, just be careful with that and work it very slowly. You can get it, and if you multiply, you take 4 divided by 7, you get 0.571. All right, the third problem I want to work, I have a 2 kilogram disc right here. It's traveling at 3 meters a second. It's going to strike a 1 kilogram stick of length 4 meters that is lying flat on a frictionless surface. Assume the collision is elastic. Keyword elastic, because then we know kinetic energy is conserved. And the disk does not deviate from its path after the collision. Find the translational speed of the disk and the stick and the angular speed of the stick after the collision. The moment inertia of the stick is 1.33 kilograms meters squared. All right. So we know that. We'll go ahead and write that down. I is equal to 1.33 kilograms meters squared. All right, a couple things we know here. We know kinetic energy initial must equal to kinetic energy final. That's because it's elastic collision. We also know that linear momentum must equal to final momentum. And we also know that initial angular momentum must equal to final angular momentum, because there's no torque being applied to this system, or excuse me, I shouldn't say it. There's no external forces being applied to the system here. All right, so let's go ahead and do this. We'll do our linear momentum first. I will have the mass, which is the 2 kilogram. We'll multiply it by its velocity of 3. That must be equal to the mass times the velocity of the disk plus the mass of the stick times the velocity of the stick. That's our first equation right there. Now I'll go back and do angular momentum. It's going to be the mass of the disk, which is 2, times the velocity, which is 3, times the distance it is from the rotational point, and the distance here is 2, must equal to, make that equal sign a little bit better, must equal to 2, write a little bit better, hang on, give myself a little bit more space, is equal to the mass of this, 2, times the distance it is, which is 2, times the velocity of the disk, which we do not know, plus the moment of inertia, times omega. Okay? Now again, you do not have to include the velocity of the stick, because the distance from its rotational point is 0. So that's our equation number 2. All right, and then we can do our kinetic energy conservation. We can do 1/2 the mass of the disk times its velocity squared must equal to 1/2 times 2 times the velocity of the disk squared plus 1/2 times the moment inertia, 1.33 times omega squared plus 1/2 times the mass of the stick times the velocity of the stick squared. That right there is your kinetic energy equation here. So that's our third equation. Alright, so if you notice here, we have how many unknowns? We have one here, and one here. We have three equations and three unknowns, so obviously we can solve this. I'm going to take the first equation and we're going to start simplifying it. So here I would have 6 is equal to 2VD plus VS here. I'm going to take this equation and solve for VS. So VS here is equal to 6 minus 2VD. I'll circle that in blue. That's going to be one we're going to end up substituting back in. We will take the second equation, we'll multiply it 2 times 3 times 2, that's going to give me 12 is equal to 4VD plus 1.33 omega. We will solve for omega, and we do that division, we will get omega is equal to approximately 9 minus 3 VD. Rounding a little bit, but that's pretty close. Alright, so now let's take that, we're going to put that back into the our energy equation here, and let's see what we got here. The 2's cancel out, that gives me 9 is equal to, this cancels out here, and then we got VD squared here, so we'll make that VD squared plus this value here, that gives me about 0.665. I'm going to substitute back in omega of 9 minus 3 VD squared plus 1/2 here, and then VS we put in here, 6 minus 2 VD squared here. Alright, at this point you'll just have to solve for VD, and you can find out that VD will equal to 2.333 meters per second. And then once you know VD, go ahead and put VD back into this equation here, and you will find out that omega will get you 2 radians per second. And then if you want VS, take your VD, put it back into this equation here, and you will get VS is equal to 1.333 meters per second. Alright, again, this problem's pretty tedious, but again, just when you do these, make sure you take note of what's given. You got elastic collision, so you can use all three of your equations here, that your kinetic energy is conserved, your linear momentum is conserved, and your angular momentum is conserved. Alright, I hope this video was useful. I wish you guys the best of luck.